Students, today we are going to do our first lab, Introduction to Scientific Measurement 1, the great conversion scavenger hunt. So we're going to talk about scientific measurement. In lecture, we're going to be doing some, looking at some scientific literature and things, but right now we're going to talk about scientific measurement. So we're going to start out talking about how measurement is kind of concerned with two things. How big is the thing we're measuring? Because an atom is very small. But, the Earth is very large. So we need numbers that can deal with those differences. Also, we are concerned with what instrument are we using to do the measurement. So for example, in an auto factory, where the parts have to be super precise, they'll use lasers or some very, very expensive instrumentation to make sure those parts need to be with maybe 1,000th or 1,000,000th of a centimeter in order to be correct. So you're concerned with what is the size of the thing you're measuring, what tools are you using. So we're going to talk a little bit about that. So I've got a book here, and I am using a simple ruler, and we're going to use centimeters. Do you know that us and Liberia are the only two countries in the world that are still using inches? Everyone else in the world is using centimeters. And it, as you'll see in your next lab about the metric system, it's led to some pretty big disasters, but we won't talk about that now. All right, so with this, I am measuring the length of the book. And the length of the book is 28.0 centimeters. I am saying that I know within 1/10 how long that book is. What if I said it was 28.003? This would have 5 significant figures, and I would be saying I know to the tenths, hundredths, to the 3,000ths of a centimeter using this instrument. This is not possible with the tool I'm using. So remember, we're concerned with the size of the thing we're measuring and what instrument we're using. With this instrument, tenths we can be pretty sure about, but hundredths and thousandths, I don't think so. So the length was 28.0. Now I'm going to do the width. And if we look at the width of this book, the width is 23.2 centimeters. So the width is 23.2 centimeters. Length, width. Now let's look at the height. Okay. How high is this book? And it is 3.4 centimeters. 3.4 centimeters. We're also today going to talk about significant figures. Looking at these numbers, this number here has 3 significant figures. Now, you might say, well, it's got a 0. Does that really count? Is it necessary to put that 0 there, or did I put it there because I knew to the 10th of a centimeter that the measurement was 28.0? It is not necessary to have that 0, so that 0 we would call a significant figure. Here, 23.2 also has 3 significant figures. We'll call them sig figs for short. And there's going to be a lot of practice with sig figs in this lab and another lab, and sig figs will come to haunt you if you don't pay attention. So try to kind of get in your mind that when we measure things, the significant figures are very important in accuracy. Okay? The height, 3.4 centimeters, only has 2 significant figures. Now, I'm going to, on the calculator, put in, we're going to find how many centimeter cubed? So 28.0 times 23.2 times 3.4 equals, and I'm going to put all of the numbers that show up on the calculator. Okay, so the volume is equal to 2208.64 according to the calculator. How many significant figures are there in this number? This number has 6 significant figures. Now, a rule is that your answer can only have the number of significant figures of the least accurate data point. 3 sig figs, 3 sig figs, 2 sig figs. This answer can only have 2 significant figures. How do we figure out then what are we going to do here? Okay, because it has 6 now. So 2 significant figures would be a volume, and we always have to put our units. 2,200 centimeters cubed. 2 significant figures. These zeros are only there to place the decimal. They're only there for that. They're not telling me we know that accuracy. Now, another way to write this, and we will be talking about scientific notation in a second, is to say 2.2 times 10 to the third centimeters cubed. 2.2 times 10 to the third. Our data point with the least number of significant figures was this one, the height of 3.4 centimeters. And so our answer is 2.2 times 10 to the third centimeters. Now, let's just say that instead of this being 3.4, that I was able to measure it much more carefully, and this was 3.41 centimeters. Now I have 3 significant figures. We'll do the math again. So we've got the 28.0. 8.0 times 23.2 times 3.41. That gives us an answer of 2215.136 centimeters cubed. Now we can have 3 significant figures because our data point with the least number was this, which is 3 significant figures. So how would we write this number? Of course, I had to get a number where there was a 5. So just as a rule, if there's a 5, we're going to round up. Okay? If there's a 5, we're going to round up. So we would then call this number, instead of 7 significant figures, we got to get it down to 3. We would call it 2.21, 2.22 times 10 to the third centimeters cubed. We could also call it 20 centimeters cubed. 3 significant figures. This 0 does not matter because it's just placing the decimal, telling you you're talking about thousands. You're not talking about hundreds, you're not talking about tens, you're not talking about 10,000s, you're just talking about thousands. Now, we will get a lot of practice with this, so don't worry if right now things are a little bit sketchy in your mind. Okay? All right, let's look at these graduated cylinders for a minute. This graduated cylinder is 1,000 milliliters or 1 liter. You know when you get a 2-liter pop It's like 2 of these. This is a cylinder, so it looks like, wow, this looks really like a lot of pop to drink. But this would be, 2 of these would be like a 2-liter pop. Okay. These gradations are, let's see, 950. So each line is 10 milliliters. I'm looking at this graduated cylinder. It's a 500 milliliter cylinder. Each line is 5 milliliters. This is a 50 milliliter cylinder, and each line is 1 milliliter. If I had a bucket of water, a large bucket of water, which one of these would I use to see how much water I had? I would use this for that quantity of water. The size and the tool. If I just had a little bit of water, you know, a little bit of water in here, I would probably want to use the 50 ml one because it's accurate to 1 milliliter. Each mark is only 1 milliliter. Here, each mark is 10 milliliters, so there's a lot of estimating. But when you have a huge amount of water, you would want to use this. So remember, the size, what you're measuring, and the size of what you're measuring and the tool you're using are important in measurement. It's very important. Okay, so with this one, I could maybe be accurate to, you know, 1 milliliter. With this, I can be accurate probably to 1/10 of a milliliter. With this, I might be accurate to 100th of a milliliter. This one here, which is a 10 milliliter, which goes to the 10th, I could possibly be accurate to the 1,000ths of a milliliter. But I would have to have a very small amount of water that I'm measuring. Now, when you're giving a baby medicine, it is very important that you have the right unit. If you think you're supposed to give your baby 2 milliliters of penicillin, you wouldn't want to use this to measure the penicillin. Okay? You would get a syringe. But when you read in our metric system lab, the next lab you're doing, you'll see a lot of medical mistakes have been made when someone thought the measurement was in teaspoons or was in fluid ounces when it was really in milliliters or even some smaller measurement. So measurement is really kind of a vital, understanding measurement is kind of a vital skill that you need in life. You really need to understand how measurement works. Okay, so that was our first topic, just scientific measurement. Now we're going to spend a little bit more time on significant figures. Okay, I'm going to put some examples up here. And again, well, let's just say that there was a rally in Washington. Let's say there was a rally and somebody said, at that rally there were 857,325 people. If somebody makes a claim like that, would you believe it? That's really kind of ridiculous when you've almost got 1 million people and you're saying, you know, down to the person how many people were there. Impossible. Impossible. Okay. You would want this estimate to come in around 900,000, which means, hey, I know there was between maybe 850 and 950,000 people there. But to say you know down to the person, what if someone's in the porta potty going to the bathroom? This number is ridiculous. 6 significant figures saying you know down to the person. This has 1 significant figure saying you know probably within 100,000 people about how many were there. And you know that politicians and all these people always overestimate their crowds and so on. But I actually was watching the news once when a group claimed there was a number like this at their rally. And I knew right away, these people are not credible. Okay? So, significant figures are very important, showing that you're kind of an educated person. So let's see. The number 100. How many significant figures does that have? does that have 3 significant figures, or does that have 1 significant figure? And this is why whenever you're doing measurements in this class, you try to get the most accurate measurement you possibly can. Okay? The number 100 tells me the real number is somewhere between 51 and 149. I am only sure 1 significant figure. Now, if you wrote the number 100 point, you've got the decimal point there. Now you're saying that I know that this number is accurate within 1, that the actual number is somewhere between 99.5 and 100.4. This has 3 sig figs. And this only has 1. Did I need to put that decimal there? I did not need to. If I have a number like 100.0, let's just say we're measuring milliliters. Whenever you write a number in science and there's a unit involved, make sure you have the unit. Again, with the baby medicine, is it in cc's? Is it in milliliters? Is it in ounces? You need to know what the unit is. This number here, these zeros are not there to place a decimal. These zeros are here to tell you, I measured this very accurately. I measured it with a very precise instrument, and I know it's within 100.0. I know it's within 1/10 of a milliliter that I'm correct. Okay? All right, let's look at a number like 26.0. Oh, how many sig figs in this one? This one has 4. Okay. 26.0. Did I put the 0 there because I needed to place the decimal? No, I put the 0 there because I was accurate to the 1/10 of a milliliter. 3 sig figs. Let's try a number like 1.0370. This is a very accurate number. Tenths, hundredths, thousandths. I know to the 10,000ths of a milliliter, you know, with all the COVID and they're trying to get the vaccine and there's all these biotech companies doing all this very precise measurements. They need numbers accurate to the 10,000ths of a milliliter, 100,000ths of a milliliter. This is a very sophisticated instrument that could get something this accurate. It has some zeros. These zeros are not here to place the decimal. These zeros are here to tell you how accurate the number is. So 1, 2, 3, 4, 5 significant figures. This is a very accurate number. Now let's look at numbers less than 1. How about 0.00417? This number is less than 1. Are these zeros significant, or are those zeros there to place the decimal? These zeros are there to tell you that it's 417 10,000ths of a milliliter. This number has 3 sig figs. Now, if the number is 0.000417, this number here, this 0 here, matters. Now I'm even more accurate. This 0, I didn't have to put that. I put it because I measured so accurately. And now this number would have 4 sig figs. So kind of a rule for numbers less than 1, you don't count any zeros that are before an actual whole number. I didn't count these. I just started counting at the first whole number, and anything after that, we call it a significant figure. Significant meaning we measured it that accurately. This measurement was super accurate, done with a very accurate instrumentation. And so anytime you're measuring in science, you want to be as accurate as possible. Because if you get sloppy and you know that it's 100.0 milliliters, but you only say 100 because you don't want to put the 0.0 part, you've gone from one significant figure in your answer. You could have had 4 significant figures in your answer, and now you've only got 1. Okay, so this one has 4 sig figs. Let's do another one. Let's do 9.0010 milliliters. How many significant figures? There's a number here. So these zeros are not placing the decimals. These zeros are telling you accuracy. So 9, this is a number greater than 1. Okay, remember, we don't count the zeros before a number, only if the number is less than 1. Okay, this is a number greater than 1. All of these count. This has 5 sig figs. Now, in today's lab, I'm going to be taking measurements. You normally would be in here taking the measurements, but I'm going to do all the measuring. I'm going to give you the numbers. You're going to have to figure out when you multiply these numbers or use these numbers. In the data, you will look at what is the least number of significant figures. Let's say the least accurate number has 2 significant figures. Remember, your final answer can only have 2. So you have to make an adjustment at the very end. Not in the middle, but at the very end, you would cut it down to whatever number of significant figures was required. All right, our third little mini lesson right here, and I'll keep some of these numbers up so we can use them. Let me erase some of this, is scientific notation. Okay, scientific notation. Now, on your phone, you have a calculator function, but there's also an app where you can get the scientific calculator, and you could definitely use that, or you can use a scientific calculator like this. So when in your quizzes, you're going to be asked to put numbers in scientific notation or put answers in scientific notation. I'll just show you on the calculator. So what you need to do, first of all, is figure out how many significant figures the number has. This number only has 1 significant figure. When you would write this in scientific notation, your answer is going to have 1 significant figure. This is 100. We would say 1 times 10 to the second milliliters. Why 10 to the second? Because theoretically the decimal is here. We know the number's not that accurate, so we didn't write the decimal. We go back 2 places, 1 times 10 to the second milliliter. Doing it in your calculator, you put in 1, and then on this calculator it has E somewhere, EE. Okay, so 1, and you push the EE, and then 2 zeros show up. 1 times 10 to the second equals 100. 1 EE, this part is the EE, and then you put the 2. What a lot of students do is they'll put 1 times 10, then they'll put the EE2, so they're always off by 10. And you can guarantee on the quizzes that I'm going to have that answer on the quiz as well. So if you put 1 times 10 and then EE2, you have introduced another 10, so you're going to end up with 1,000, which is not the correct answer. Now, when you have a number like this, 3 significant figures, writing it scientifically, 1.00, move this 2 places back, times 10 to the second milliliters. You need to include all the significant figures when you're writing in scientific notation, because you want to You don't want to take accuracy away from your number. You always want to keep the accuracy. If there's 2 sig figs, you write 2. If there's 3, you write 3. How many sig figs? This one has 4 sig figs. 1.000 times 10 to the second milliliters. You're telling them this is a very accurate number. Okay? 3 sig figs. I'm going to move this only one place. 2.60 times 10 to the 1. However many places you move the decimal, that is the exponent. Okay? That is the exponent. Oh boy, now we've got this number. How many places am I going to move the decimal? I forgot to say with scientific notation, there's always only one number before the exponent. I mean, you're always going to bring this down to the ones place. So let me explain that. With the 6 sig figs, if I told you to write this number in scientific notation, whoops. If I told you to write this number in scientific notation, I'm going to just write 1.0370 times 10. Did I move this decimal at all? I did not. So how many places did I move that decimal? 0 places. So that would be a 0. Now, if the number is less than 1, now you're going to use what we call negative exponents. Again, we only want one number before the decimal, so this number becomes 4.17. We have to include all the significant figures. Now, where's the decimal? It's here, and we're bringing it here, so we go 1, 2, 3, 4. 4.17 times 10 to the negative 4. When you are moving to the right, we say a negative exponent. When you are moving to the left, we use a positive exponent. You can go on Khan Academy if this is confusing. There's a lot of great lessons on significant figures and on scientific notation that you can practice with. All right, a number less than, now we've got 0.4170, 4.170. We want to include this O because it is significant. Again, we're going 3 places to the right. Oh, we're going 4 places to the right. Sorry about that. Times 10 to the minus 4. Always want to include the units. This could be centimeters, this could be inches, this could be miles, this could be anything. Okay, let's do our last one. 5 sig figs. Am I moving the decimal at all? No. So it's going to be another one times 10 to the 0, 9.0010 times 10 to the 0 milliliters. Now, why do we need scientific notation? In science, we deal with massive numbers. Like the weight of the earth is just a massive number. In science, we deal with tiny numbers, like the mass of an atom of water. The mass of an atom of water has 23 zeros in it. So it's like 0.000000, and it just keeps going, and a 3 at the end. You can write that number as 3 times 10 to the minus 23 grams. Much easier to write than 23 zeros. When we're talking about the mass of the sun, we're talking about a monstrous number. But we're going to use scientific notation so that a lot of part of that number is in the times 10 to the negative 3 or times 10 to the whatever. So let me see our last topic. Oops, okay, so I found the mass one. So Sirius, the brightest star, is this many miles away, 51, 200. This is how many miles away the star Sirius is. Even our sun is 93 million miles away. That's a big number. How many significant figures? Just 3. Let's see when we make this scientific notation. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in scientific notation, 5.12 times 10 to the 13 miles. What's easier to write, this or this? What's easier to understand, this or this? Okay. What's easier to write? So in science, we need scientific notation for these massive numbers, for these tiny numbers, because the size, and there's a really neat little video in class that you'll see that shows just how big and how small things are in science. All right, our last topic before we go on our exciting scavenger hunt is dimensional analysis, and it sounds very complicated. It sounds very scary. Wow. Okay, but it really isn't. Okay, so this is dimensional analysis. You may remember this from chemistry, but really it's, so our 3 topics were scientific measurement, that was 1, and 2, including sig figs, significant figures. And 2 is scientific notation, where we use the exponents for very small, very big numbers, and 3 is dimensional analysis. So dimensional analysis, very simple, okay? If we want to know, oops, how many dozen 6 eggs are, what we have to come up with is an equality that relates eggs and dozens. So, and algebra is always going to come back and get you. So try to just kind of realize if you hated algebra, you got to kind of get algebra back a little bit. If I need to come up with something that relates eggs and dozens, so of course, 1 dozen eggs is 12 eggs. So 1 dozen is 12 eggs. 1 dozen and 12 eggs is the same thing, 1 dozen eggs and 12 eggs. That's an equality. We can put that equality here, and now we can see how many dozen 6 eggs is. So do we want to put 12 eggs here and 1 dozen here? 1 dozen here. Then we end up with eggs squared over dozen. No, we don't want that. We want to put 1 dozen here and 12 eggs here. Now we cancel the eggs. 6 over 12, 1/2. So we can say 1/2 dozen, or we can say 0.5 dozen. Okay, either way. So with dimensional analysis, you can start with miles and get it down to centimeters if you want. You can start with centimeters, get it up to miles. You can start with anything. Let's see. Let's pretend I have 36 eggs now. 36 eggs. Okay, and I'm doing eggs and dozen because it's something everyone knows. 1 dozen is 12 eggs So 36 eggs is 3 dozen. Now, what happens to students when instead of eggs and dozen, we have moles and something else, or we have kilometers and inches? People just fall apart. But just think of it as simple as this. It's just, in this, there's something that's equal that's getting us to the answer. Okay. Now, let's do another one that's very familiar. Let's say we have 20 people, and we want to know how many toes. Okay, how many toes is there? So we need to relate something with a person and toes. So we want to get rid of people, so we'll have 1 people, which isn't great English, but 1 person. 10 toes. 20 times 10. 200 toes. Does that make sense? Sometimes you're dividing by a number, sometimes you're multiplying. It just depends what you're coming from or going to. All right, so let's say that we want to know that we made a measurement that was 15 centimeters. We measured something and it was 15 centimeters. And we want to know how many miles is 15 centimeters. Oh, by the way, how many significant figures are in this number? 1. So our answer can only have 1 significant figure. Your answer is limited to your data. So the equalities don't count toward that, only the number here. So how many significant figures is our answer going to have? It's going to have 2 because our measurement only had 2. If our measurement was 15.0 centimeters, this would be 3 significant figures, so our answer could have 3. So if you're measuring something and it is 15.0, write down the 15.0. Don't write down 15. Now you've got 1 more significant figure. Your number can be that much more accurate. When you're multiplying a lot of numbers, you end up with big answers, and then you have to trim it down to your number of significant figures. Okay, so we want to get from centimeters to miles. So maybe some of you know that 2.54 centimeters is equal to 1 inch. Maybe not. This is an equality. These things are equal to one another. And most of us know that 1 foot, or 1 feet, is equal to 12 inches. Remember, we want to end up with miles, so each time we cross something out, we want to be closer and closer to miles. Now we know that there are 5,280 feet in 1 mile. Get rid of feet. Now we've got our answer in miles. Okay? So when we do the math, it comes out to a very long, drawn-out number. Now, centimeters to miles, are we going to have a number less than 1, do you think? Yes, we're going to have a number less than 1. Let me just do the math here. So 15 times 1 times 1 times 1, okay, divided by 2.54, and divide that by 12, and divide that by 5280. We come up with this as an answer, 0.000, 4 zeros, 93206 miles. Okay, very small number. How many significant figures were in our data point? 2. Our answer can only have 2. This is 932. If this was 936, we would round that up to a 4, but it's not. So our final answer is 9.3 times 10. Let's see. 1, 2, 3, 4, 5 times 10 to the minus 5 miles. That's our final answer. 9.3 times 10 to the minus 5 miles. This is why metric, in 1989, Congress made a law that the United States of America was going to metric. Of course, politicians, they never said when. So someday we'll go to metric. But remembering all this 12-inch, 5,280, in metric it's all tens. You know, 100 centimeters is 1 meter. 1,000 meters is a kilometer. Everything's by tens, so it's much easier to work the math, and hopefully someday we'll go to that, but that's another story. Okay, so now we've introduced some basic things about scientific measurement, and we will be doing, in lecture, you'll have some other exercises on that. But right now we're going to start our scavenger hunt. And we're going to be hunting for these numbers. We're going to be hunting for these numbers here. These are just numbers, and they have some significance. Okay? So what we want to do is measure some things in multiple ways so that we can see if they match any of these numbers. Now, all of our answers, in order to be legitimate, we want our answers to be within 10% accuracy. And the way you tell that is by taking what you measured minus the actual, divide by the actual, times it by 100. If it's a number less than 10%, you're good. You can keep that. All right, so let's start with the volume. We've got 1, 2, 3, 4, 5, 6, 7 possible numbers we can find a match for. What we're going to do is we're going to measure this same quantity of water, which is 0.80 quarts. We have 0.80 quarts. That is how much water we have. We're going to take that same amount of water and we're going to measure it in different ways. Okay? We're going to measure it in different ways. Let's pour it into our largest graduated cylinder and see how many milliliters. By the way, how many significant figures is 0.80 quarts? That's 2 significant figures. 0.80 quarts is the same as 700, and I would say it's 700, not quite 760, so 759 milliliters. That's how much this amount of water. 0.8 quarts, it's the same water. We measured it a different way. Let's see how many cups this amount of water is equal to. If we look on the cups, this is 3.5 cups, so that would be 3.5. So I'm going to say it's about 3.2 cups. Okay. How many sig figs in this number? 2. This one has 3. This one has 2. Let's see. We already did quarts, so let's see how many pints this is. Let's see how many pints. I've got 1 pint. Now I've got to get rid of this. I've got 1 pint. Remember, I'm using the same amount of water. I am measuring it different ways. So far, there's 1 pint. This is a half of a pint here, so 0.5, and this would be 0.75. So this would be 0.75. Boy, let me put it down for a minute. All right. So this is 0.5 of a pint, and that is 0.5, 0.75, so that would be 0.25 more, so 0.625 here. So I would say we are about 0.6 pint, 1.6 pint, because remember I already had 1. Okay, and let's go back to liters. So that same amount is 0.76. This is 1 liter, 0.76 liters. Okay, now, these are like magic numbers here. These are like magic numbers. You're going to use these numbers. You're going to do quarts per milliliter and milliliters per quart and see if there's a match. You're trying to match. This is called the Great Conversion Scavenger Hunt. You're trying to figure out what these numbers mean, and you're going to use the data we just made. So why don't we do quarts to milliliters, and then we'll do milliliters to quarts. So we've got 0.80 divided by 759. Let's try and see what that equals. 0.80 divided by 759. And that is equal to 0.00105. This was quarts. This was milliliters. Quarts to milliliters. Okay. Does that match any of these numbers? No, it does not match any of those numbers. Let's try milliliters to quarts, and let's see what we come up with there. We have 759 milliliters, 0.8 quart. Okay, so let's try 759 divided by 0.8. 948, whoops, 0.80, 948.75. How many sig figs in this number? 2. There's 3 in this. Our answer is limited to 2 significant figures. So what would we round that off to? 950. 2 significant figures, milliliters per quart. Is that within 10% of that number? It actually matches exactly. You have a match. Now you're going to fill in your table. So I'm going to get the projector going, but in the meantime, we'll do some other measurements. Okay? We'll do some other measurements. Remember, I tried it one way and it didn't work, and then I tried it the other way and it did work. These are the numbers that you want to match, or that you want to use to try to match any of these numbers. We had a match with 950. let's look at our lab for 1 second. And let's see where we would write our data down. So you have a data table. The number we matched this time was 950. So you would write 950 here. The object we used was water. We used water. Our calculated conversion factor was actually 950. And the calculation you would show here would be exactly this. 759 milliliters divided by 0.80 quarts is equal to 948.75 milliliters per quart. But when we consider the significant figures, we got 950. That is what you would put here. Okay. That is what you would put here. These numbers that are on the board, you are only going to use these numbers here to match any of these volume numbers. Okay? To match any of these volume numbers. You're only going to use these numbers right here for this part. So you're looking for a scavenger hunt. You're looking to find conversion factors. You're looking to find things that equal these numbers. So these volume. Let's do the mass part. Okay? Now we're looking at a different set of numbers. We're looking at mass. So I'm going to erase this. Okay. I'll erase those numbers. Now, let's look at, I've got a bead here. I've got a bead here, and I am going to weigh this bead 3 different ways on this very accurate little scale. Okay, so I'm going to turn it on. I'll make sure that it goes to 0. It's at 0.0000. I'm going to, it just went to 0.01. Okay, my breath will even make it move a little bit. I'll put the bead on, and I am going to start over and tare it. Okay. All right. And I got to take the top off or else it won't weigh anything. So that's why I didn't get a measurement. All right. Right now, it is measuring in the unit of carats, you know, like a carat, a 5-carat ring or whatever. That bead weighs 14.75 carats. Okay. I'm going to change this now to grams. That bead weighs 2.950 grams. Now I'm going to change it to ounces. That bead weighs 0.1041 ounces. Look at these numbers. How many significant figures? This is an expensive scale. In fact, we lock this scale up because people in a certain business want scales like this. So we don't, keep it out. 4 significant figures. This is to the tenths, hundredths, thousandths, 10,000ths of an ounce. This is very accurate. Okay, so those are 3 numbers we have. This was all the bead. Okay. Let's use grams and ounces and see if we can come up with a match. Okay, let's use grams and ounces. So I've got 2.950 grams is the same as 0.1041 ounces. So let's do the math on that. 2.950 divided by 0.1041 equals 28.33813. How many sig figs am I limited to in my answer? I'm limited to 4, so I have to now bring that number to 28.334 because grams per ounce. I look at this number, it happens to match that one right there. We go back to the data table. The number we were trying to match, 28.3. The object was the bead. What you calculated is the 28.34 grams per ounce, and your calculation is going to be this right here. Okay? Now, we need a couple, so hey, that worked. What you can do is you can try ounces per gram too. That might match something up here. You don't know. Every time you use something, make sure you try it both ways. You try grams per ounces, ounces per grams. Okay? We have got the bead and we have got 3 numbers. You can use these 3 numbers. Carats per gram, grams per carat, carats per ounce, ounces per carat, grams per ounce, ounces per grams. You can try it all different ways. Remember, you're on a scavenger hunt and you're trying to match these numbers. Let me, with my shoes on and a heavy coat and a microphone, come and weigh myself in 2 different ways so that we can get another set of numbers for mass. So I'm going to step on this scale, and this is in pounds, and it is at 161 pounds. Okay, 161 pounds. And now I'm going to step on this scale, which is in kilograms, 73.7 kilograms. So we've got 2 more numbers. This is Professor Hartshorn. And I've forgotten, I was 161 pounds. And was it 73.7 kilograms? Okay. This is some more data that you can use in the mass part of the lesson. This is some more data. Okay. So your data for the mass. Now, can you mix the bead and the... No, you can't mix those 2. All right. This is one set of data. Another set of data, 3 significant figures. Great. Remember, your answer should have 3 significant figures. This is your data for the mass part. Okay. We had our data for the volume part. And again, each time you get a match, you're going to write your match in the data table. Okay, each time. We've got one more set of data to get because we have to also do length. We're doing length, we're doing mass, we're doing volume. So just like, oh, and remember, if you're not sure, like the 2 we did, they were very close, so we knew they were within 10%. But if you're not sure they're within 10%, you can use this formula, the measured minus the actual over the actual. So let's say for this one we had, let's just pretend it was like 26.2 minus 28.3 over 28.3 times 100. And if that number was like 4.3, we know we're within 10%. If you have a number that's kind of far off, just make sure it's within that 10%. If you're looking for the A on the lab, okay? And make sure you pay attention to significant figures too. One more set of data And I'm just going to tell you right now that I measured this lab table. And I measured it in several ways. I measured it in meters, and it was 1.67 meters. I measured it in centimeters. It was 167 centimeters. I measured it in inches. It was 65.5 inches. I measured it in feet. It was 5.5 feet. And I measured it in yards. It was 1.83 yards. Okay. Again, remember, we're measuring the same thing in different units. That's why units are so important. Okay. I measured that table. I measured it 5 ways. You're going to do the exact same thing with these numbers. Try meters per centimeter. Try centimeters per meter. Try inches per foot. Foot per yards. Inches per yard. Try different combinations to get a match. Okay? So let's see how many matches you need to deal with. There's 1, 2, 3, 4 per page, 4, 8, 12. You're going to have 12 matches. Okay? So on your lab handout, there's more than 12 numbers up here. Okay? But I want you to have something from each category as well. Okay? We've already done one from volume and one from mass. You get one from length. And I want you to, mix it up a little bit. Pay attention to significant figures and pay attention to filling out the data table correctly. The beginning of the lab is basically a lot of information like I gave you from the lecture in the beginning, but it's just more additional. Again, Khan Academy, significant figures. Khan Academy, exponential functions. Khan Academy, dimensional analysis. If there's anything you need to get more practice on. The point of this lab is to get you thinking about significant figures and get you working with different units. And once you get your 12 matches, you're done. You'll turn it in. It's great. You can write on this. You can print it out and write on it. Or you can just type in your answers, on a Word doc. This is a Word doc. Make sure when you save your labs, you put your name in the saved document, just so that I know. Also, whenever you're doing answers in this class on these labs, if you will use a different color font, that really helps me when I'm grading. So this lab is basically a data table, but other labs will have a lot of words and so on. So just make sure you use a different font. All right, have fun. Thanks.